Good morning, good afternoon, and good evening to all the software testing enthusiasts around the world. Thank you for tuning with us for the A4Q Testing Summit. Today we have with us Adam Roman. So Adam will be giving us a presentation on a beautiful title, actually, Kill Them All. So it's about mutation testing for quality services. That's a very innovative title, I would say, Adam. So just to introduce yourself, Adam, you're a research and teaching fellow at the Institute of Computer Science and Computer Mathematics at Jagiellonian University, where you have been conducting research, lectures, and seminar on software testing and quality assurance for many years. So you are the co-founder of the software testing postgraduate program at the university. Your research interests include research on new software quality metrics, mutation testing, which is our topic for today, and effective test design techniques. As part of the Polish committee for standardization, you've collaborated on the international standard for the ISO and the IEEE 29119, which sets a standard for software testing. So we are very glad to have you here with us, Adam, and very keen to actually learn about mutation testing. So I'll leave the floor to you.
Okay, thank you. All right. So thank you for inviting me at this conference. As Loveless said, I will be talking about killing, that is killing mutants in mutation testing. So here's a short introduction of myself, but Loveless already did it, so I will skip it. And I will go straight to agenda. First, I'd like to talk a little bit about mutation testing itself, then about a variant of this technique, or maybe the approach which uses mutation testing to detect defects in software defect prediction. So it's called mutation analysis. Then shortly, briefly, I will talk about tools for mutation testing, and then some conclusions about both pros and cons of using this technique or this approach. So what is mutation testing? In a classical test approach, let's say in a typical black box testing, we have the system under test. We have some specifications, some requirements, which are the test bases, that is, which are the base on which we design test cases. And we also define expected results based on specification. We use this test case to test the software and then compare expected and actual results and see if it's okay or if it's not, if the test fails or it passes. So the focus here is on this black box, on the software or system under test. And we assume that test case is just fine, it's correct, it's with no errors, which may not actually be the case. And it may be problematic, right? Because, for example, imagine that we automate tests, and this test case is some kind of a test script. So test script is also a piece of code. So it can contain defects just as can system under test, right? So in order to be accurate about all this thing, we should actually test not only the system under test, but also our tests which we use to test the system. So because we don't know if the tests contain any defects, we should write tests that test the tests, right? But now the problem occurs again, because when we write tests that test the tests, these tests can also contain defects. So we should test also these tests. So the next natural step would be to write tests that would test the tests that test the tests. And ad infinitum, right? Then we should add tests that test the test, that test the test, that test the test, and so on, right? So of course it's impossible. We can't do this. We can't go in infinity with this process. But the problem remains, right? The test cases may contain defects. So what can we do about it, right? And the answer is mutation testing. Mutation testing cuts this infinite process at level 0, at the level of our original test cases. We don't have to write any extra test cases that test some other tests. Mutation testing directly verifies the main goal of mutation testing is to verify the quality of test cases. So the interesting thing about mutation testing is that it tests the test with no need to test the mutation testing process itself. So we don't have this unfortunate infinite sequence of tests. So what is a mutation testing? Now it's time to define the process. Mutation testing is a technique which introduces some really small changes into a program and then observes whether the existing test cases are able to detect these changes. For example, if we have some decision statement, like if x greater than y, then do something, and we change this relational operator greater than, we change it to greater or equal, right? So it's a defect because this is the left one is the correct one, so it should be greater than, but we change it to something wrong, to greater or equal. And then we compile this program with this intentionally inserted defect, and we run our test on this so-called mutant. Program that is changed in this way is called mutant. So we check whether the tests, if there is any test case in our test suite that is able to detect this defect. So here we just changed by using so-called mutation operator. I will talk about them later. We changed something in the code into something else, and then we check if the tests are able to detect this. How it works? Let's say we have original program P, we have this mutant M, which is P slightly changed. We have some test case T, and by P of T and M of T, we will denote by these two things results of P or M on test T. So when we run our test T on the original program P, there are two situations possible. Either the output of P on T is different than the output of M with this T. So the result of original program and mutant these results are different, or they are equal, right? They are the same or they are not the same. So if they differ, we say that this mutant was killed by our test case because our test case detected something wrong, right? The expected result should be P of T, but the actual result of this mutant is M of T. It's different. We detected that something is wrong. So we killed this mutant. Our tests were able to detect it. But if no test detects it, so for all the tests we have, this result is equal to P of T, then no test detects the problem, right? Because the expected outputs are exactly the same as the real outputs. So if this situation occurs, it means that our test suite is weak because we have no tests that could detect this potential defect in the code. And now there are two main applications of this technique or approach. First, I have just told about it. First is just testing the test. So we use this mutation testing. We count this so-called mutation score, the fraction of mutants killed by our test, to test the test suite, to check what is the quality of our test suite or our test set. And if we have the situation that no test detects a given mutant, no test is able to kill a given mutant, then we can add another test case. We know where the defect is because it's intentionally inserted mutant in a very particular place in the code. So we know where is this potential problem, and we can easily write the additional test case that could kill this particular mutant. So we somehow make our test suite stronger. And that's how the quality of tests increase. But the second application of this technique is in defect prediction, in software defect prediction. We can easily use mutation testing to predict, to guess, to estimate what is the actual number of remaining defects in the code. It's a relatively simple method for defect prediction, and I will talk about it later at the end of this presentation. The mutation process looks like this. I won't go into details. I talked about this process a little bit earlier. In general, we have our program. We create mutants for this program. We can detect so-called equivalent mutants. I will talk about them later. Then we run our tests both on original program and on mutations and on mutants, and we compare results. If we killed all the mutants, it's okay. If there is a mutant that was not able to be killed by our test suite, we can add some new test cases that could do this. And then we repeat this whole process until this so-called mutation score is achieved. Mutation score is the percentage of mutants killed by our test cases. So for example, we set some threshold like 90% of mutation score, and if we achieve this 90% of mutants killed, we end the process. The nice thing about mutation testing is that this whole gray area are the activities that are done automatically by the mutation testing framework. So we don't do any manual work here. The only manual work we do is to create test cases, but we need to do this anyway, so that's not a problem. And to add some new test cases if no test kills a given mutant, for example. This whole process is fully automated. So it's a very, very nice thing about this approach. Here we have some simple example. Let's say we have original program that reads two variables x and y. If x is greater than 0, then it increases y by 1 and returns the sum of these two things. Here we have examples of three mutants. In one of them, in M1, we change greater to less than. In the second one, we replace one variable, right? In line 3, we replace y with x. And in the third one, we add a minus operator to this returned value. So we have these three test cases, these three mutants. And now let's say we have a test case with x equals to 5 and y equals to 5. So we see it's easy to see that the expected result should be 11. And now when we look at the results for all these three mutants, we see that for M1, the result is 10. For M3, the result is minus 11. So these are not equal to 11. So they are killed. We detected some problems. So our test case was able to detect these mutants. But for M2, the actual result is the same as the expected one. So our test case didn't detect anything wrong because the actual result is as we expected, right? It's 11, as it should be. Why is it so? Why is it so? The problem is that when we look at this code, we see that if we replace y with x here in this line 3, then if only the value of x is equal to value of y in line 3, then the result will be the same, right? Because it doesn't matter whether it's x or y. If x equals y, then the result will be exactly the same. So we, analyzing this situation, we detected some weakness in our test suite. So we noticed that for this particular situation, we should add a test with x which is not equal to y, and we don't have such a test case in our test suite, so we should add some new test case for x not equal to y, right? So we are somehow forced to add the second test case. Let's say for x equals 5, y equals 6. And now for the second test case, the expected result would be 12 here, but the actual result will be still 11 because of this x in place of y in line 3, right? So the second test case killed the mutant because the expected result was different than the actual one. Now, there is a small, let's say, problem with some mutants, because it may happen that when we do this mutation operator, we apply this mutation operator to our code, it may transform the program. It may change something like here, this red thing in the program, but the program will be equivalent to the original one. Here, look, when we replace this variable a with min val, nothing changes really in the program, because in line 2 we set min val to a. So min val and a are the same variable, right? So changing it in line 3 doesn't change anything in the program. For all inputs, both original program and mutant will return the same value. Such situation is called equivalent mutant. Equivalent mutants cannot be killed because they are by definition equivalent to the original program. Sometimes we want to avoid these situations, and there are some heuristics that allow us to detect at least some trivial equivalent mutants. So that's why in this process here, there is this step, detect equivalent mutants. If we have a lot of equivalent mutants, they impact the mutation score, right? Because it will be lower than it is in reality, because the denominator will be greater because of equivalent mutants. So we try to avoid equivalent mutants. And now about the mutation operators. There are many different mutation operators which simulate the mistakes that developers made, right? So this, for example, changing greater to greater or equal simulates a situation that could occur in a real life, right? The developer could make this error and write greater than or equal instead of greater than. But not all mutation operators are useful. There may be some so-called trivial mutation operators. For example, there's a quite old tool called Jester, and it uses in particular two operators. They change constant 0 to 1, and they change constant true to false. So usually when we change true to false, probably any test case that will go through this line in which we made this change will detect that something's wrong, because we will take a wrong path in the code and something wrong happens. So it's easy to detect such things. So mutants for which almost every test case kill them is called equivalent. Is called trivial mutant. So the whole point in mutation testing is to design and use good mutation operators, strong mutation operators. Here are some examples of simple operators related to arithmetic operations, relational operations. So we can change plus to minus, we can change y to absolute value of y, and so on. These are simple changes. We can also make mutations on the object-oriented level. For example, we can delete the method execution. We can change the access type to a field or to a method. We can delete the super keyword, and so on. So these operators doesn't only operate on low-level code, on single characters in the code. They may be a little bit more complicated. Mutation can also be used not only for source code, but also for any other let's say, high-level process. For example, we can apply mutation to finite state machines, like here, right? For example, mutation may change a transition from one state to something to some other state. So we change the incoming state for this transition to this one, right? And this simulates some defect in the process, which can or may not be detected during our testing. Now, here is some real-life example. This table presents the results of mutation testing for one version of log4j library, and you can see here that for many classes, there are still some alive mutants, which means that the original test case suites that are related to this classes for this program, they were not able to detect everything. They were not able to detect everything, and that may be the reason why there was a very well-known failure 1 or 2 years ago. Very big critical defect, security defect, was found in log4j library, and all software that uses this log4j had to the teams had to do some hot fixes to fix quickly this problem. So this happens in real life also. Maybe if mutation testing was proceeded in a professional way, maybe such things, such critical defects, could be found earlier in the life cycle, not causing these troubles. And now the second application of mutation testing, defect prediction, so-called mutation analysis. Let's start with some practical problem which biologists have. Biologists often want to count some animals in a given space. For example, they want to count fish in a pond, let's say in a very large pond, right? So how do they proceed here? They catch fish. Let's say they caught 8 fish. They mark them somehow. Let's say they color them with some waterproof paint or whatever, and they release them into the pond. They wait for some time, and they catch fish again. They do the process again. It's called capture, recapture. So they do this the second time. And let's say in the second, during the second fishing, they caught 6 fish, 2 of which were marked, right? So we caught 2 previously caught fish and 4 new ones. So what does it, the question is, can we infer something about the total number of fish in this pond? So yes, we can do this, and the analysis is very simple. If first there were 8 fish caught and painted orange, let's say, and then in the second time we caught 6 fish, 2 of which were painted, were marked, it means that 1/3, 2 out of 6, 1/3 of the fish here is marked, and we assume that this proportion also holds for the whole pond. So for the whole pond, we also assume that 1/3 of fish in this pond is marked. So if we marked 8 fish and they constitute 1/3 of the total number of fish, then there must be 24 fish in the pond, right? That's the very simple. That's a very simple analysis. This approach is used in. It can be used in software teams where there are 2 independent teams which work on some project. Each of them detects some number of bugs in the code. There is some common set of common bugs that are found both by these 2 teams, and then we can, based on this result, we can infer about the number of unknown all defects which remain in system under test. So we assume that defect detection effectiveness should be the same for each subset of all defects. So the effectiveness of this green team in detecting all defects is the same as in detecting only defects restricted to that found by red team only. So this gives us this equation, and from this equation we can easily count this unknown x, which is the number of all defects, right? So proportion of number of defects found by green team to the total number of defects is the same as proportion of bugs found by both teams to the number of bugs found by team B, team red. So we can do this, and but the problem is here that we usually don't have two independent test teams, and we don't have money budget for doing such thing, right? So again, mutation testing comes to the rescue. We can proceed as follows. X is the number of all defects. D is the number of defects actually found by our test set. So X minus D will be the number of remaining defects. M is the number of generated mutants, and K will be the number of killed mutants. And we assume a simple fact, a simple thing, that the proportion of killed mutants is the same as the proportion of detected defects to all real defects to all real defects in the code. So K to M is the same as D to X. We know everything except X, so we can easily count. We can easily calculate X, which is D times M divided by K. If we subtract D, the number of defects found so far, we obtain the estimation of the defects that still remain in the code. Of course, there is an important assumption here, because it's a relatively simple model. Mutation operators, I said that they mimic the developer's mistakes. So if the mutation operators used in the analysis does not mimic these mistakes, are, let's say, these trivial mutants, the result may be subject to a large error. But if the operators reflect the real developer's mistakes, this estimation may be very accurate. So these are two things that we can do with mutation testing: evaluate our tests and predict the number of remaining defects. And now, at the end of this presentation, I would like to say a few words about tools. There's a really lot of tools for mutation testing. Here is some cloud of words, which are the names actually of these tools. Some of them are very popular. For example, for Java, there is a very well-known tool called PIT, testing tool. So it can be used by Java developers. It gives us the results in a very nice way. So, for example, it reports where the mutants were inserted and what were these mutants. You can see it on this in this figure. This green thing presents some mutant, and it said that this mutant number 1 was killed, and for example mutant number 3 in line 12 was it survived. So we can analyze which mutants were killed, which were survived, and based on this we can enrich our test suite so that the mutation score increases and the test suite is stronger. So conclusions. What are the pros and cons for this approach for mutation testing? Pros are as follows. It's effective, very effective, and very easy to use technique. It allows us to evaluate test cases. It can be used to detect, estimate the number, the unknown number of defects. So it can be used to in software defect prediction, and it's almost fully automated. This technique is considered in the literature as one of the most effective test techniques. And the cost of introducing tool in the organization and using this process is almost zero. You just install the tool, you just put there your test cases, your existing test cases, and that's all. You run the software, and that's all. What are the cons? Time consuming. Effectiveness depends on the operators, mutation operators used, and these tools may not always be user friendly. But all in all, at the end of the day, I think it's a technique that is worth using. It's very effective. So if you haven't ever heard about this, you may be interested in this. You may dig some deeper in the internet, maybe in some resources, and introduce it in your projects. You will see it's a very, very nice tool, very nice approach, very effective approach. Thank you very much.
Right. So thank you, Adam. It was very instructive, and it was very interesting as well in terms of mutation testing. That is something that is new to me. It reminds me of unit tests, actually, that we use right on Java using genuine framework and so on. We do have some questions and some impressions as well from our social media platform. So Francois is asking about, I found when there is a change of method where you don't validate everything in every method again for better readability. Mutation testing results in a lot of false positive. How do you handle them?
I'm not sure if I understand it correctly, because what would be the false positive here? So it would be, let's say, mutant that some test
It's
case.
not a mutant. Yeah.
Yeah, that's some test. So I assume it's like this equivalent mutant problem, right?
Yes, I guess so.
So, okay. So for this thing, there are some heuristics, because in general, detecting the problem of program equivalence is undecidable. So there exists no algorithm that could, in general, take as the input two programs and return true or false depending on whether they are equivalent or not. It's impossible. So we can only rely on some heuristics, and one of the very simple approaches for detecting equivalent mutants is to compare the compiled version of these two programs, because compilers are very smart, and they usually, when the programs are equivalent and the change is very slight, it's a very little small change, then when compiler does something with this code to optimize it and so on and so on. So usually when there are two equivalent programs, the binary versions of these programs will be the same, and that's how you detect equivalence in these two programs.
All right. So we have some clarification about the false positive from François. So false positive being you have an implicit precondition that is not written inside one method, but can be deduced from the program flow, other test cases, or code documentation. So this is what he means by false positive in this case.
But because false positive can relate not to mutants but to test cases, right? So if test case gives us false positive, it means that there's something wrong either about the test case, either about or about our awareness of requirements. So that's, I think, that's quite a different problem here, because for mutation testing, in generally, the assumption is that if we generate some mutant, and we detect, let's say we detected that it's not equivalent to the original program somehow, then the result, it must be the case that when the no test case gives us different result than the original program, then it means that no test was able to detect this change. And if the developer made this error, then it would be it wouldn't be detected, right? So that's the whole point in this mutation testing. If there are some false positives, there's always a problem, because it's always somewhere else. It's always one level higher. There's something wrong about test cases. There's something wrong about our understanding of requirements, or something like that. That's I think it's a slightly different problem.
Thank you for your answer on that. We have a few more questions flooding in. So, are there any approach that allow the tester to shorten the mutation testing time?
Yeah, one of the problems with mutation testing is that it's fully automated, but it may be really time consuming, because the mutant generation process may be long, the compiling process may be long, and so on and so on. So there are, of course, some approaches that allow us to make it smarter. For example, one approach is to put more than one mutant into one compilation and add a special variable, a special flag that would switch on and off these mutants, and it will switch on only one at a time. So we compile it just once, but then we run this program with different values for this, let's say, control variable. and this way we don't need to compile it like 10 times just once. That's one thing. Another approach is to for programs that use bytecode like Java, the mutation process can be applied directly to a bytecode, so we don't really need to operate on the source code, which is more time consuming. Another thing is that we can somehow try to order the test cases for which we because we need to execute test cases for all mutants. So the ideal thing, the ideal case would be that if we have some test case that can kill some mutants, we would like this test case to be the first one, right? If we kill a mutant in the first test case, we don't need to run all the other test cases for this mutant because it's already killed. So there are some approaches. Even this, I think this PIT testing tool in Java has some very primitive but some implemented mechanism that somehow weights these test cases and tries to prioritize them. It doesn't work very well, I think, but there are some smarter methods that may use some fancy rocket science things like Bayesian approach and or whatever. But there are some approaches here, and of course we can parallelize. We can if we are able to run something in parallel, run few mutants in parallel, then of course this can be done as well, and the time will be shorter.
Thank you for your response. And we have another question: is unit testing an implementation of mutation testing? So I found the similarity as well.
Yeah. Unit testing as such is not mutation testing, because unit testing is a test level. It's just testing the units or components or whatever. Mutation, the idea of mutation is introducing some changes intentionally to the code. So it's fault seeding. I think that's the other common term for this thing. Of course, we can do, and usually the vast majority of application of mutation testing is at unit testing level, because usually it's performed by developers on their own code, on their own functions, on their own methods, classes, or whatever. However, mutation testing, as I said before, can be applied to more than just simple code on unit level. It can be applied to high-level models like Petri nets, or like finite state machines, or I don't know, decision tables. Any formal model it can be used for any formal model that has some rules for building it, and we can then design mutation operators that can change something in this model, right? So yeah. Mm-hmm.
Makes sense. Right. One last question: how can we benefit from the result of defect prediction?
Oh, thank you very much for this question, because from my experience, I know even today there was a PhD defense of Jarek Kryszko, my PhD student, who wrote the thesis on defect prediction. And the problem is that in practice, in commercial applications, in organizations, in software houses, people usually don't do defect prediction. It's complicated, it's difficult, it's not so easy to implement, and so on. So maybe that's the reason. Maybe they just don't know that there is such a thing like defect prediction, and it's really beneficial for the company. But the trick here is that it's beneficial when your organization is mature enough to measure things that you should measure to benefit from this. Because how can it work in theory, in an ideal case? We have some process, we have some testing, we detect some defects, we have some data on defects in production, some field defects. We know how much time we spend on fixing these defects on average, what's the average cost of fixing one field defects or whatever, right? And now we can, when we are in the middle of the development, we can predict what's the number of remaining defects in our code. And we know from the historical data that there is this average cost of fixing field defects. It's usually much higher than fixing defect in the testing phase, right? Or in the development phase. That's the whole idea of this BEM curve, which we all know, right? So we can do some simulation. if we release the software today, we have, let's say, we estimate there is 100 bugs still not detected. They will probably be detected by the users. It will cost us 100 times this average cost of fixing field defect. It will be usually a large number, right? But if we wait 2 or 3 iterations more, we will detect some more defects. We can even estimate this using some other prediction models, some Rayleigh theory or whatever. There are tools for this. So we can simulate that after 3 more iterations, we will have not 100, but only 30 defects in the code after release, right? So these 30 defects will cost us, to fix them, of course, it will be a much lower number than in case of 100, right? So we can use defect prediction to make some economic simulations about our software, right? So that's one reason. Another one is, of course, quality control and all the stuff related to quality. One more thing. When we can detect defects really nicely, then we can apply this prediction to different modules, different components, and then we can concentrate on these ones that for which the model predicts that there are a lot of bugs there, right? So we can do this Pareto analysis to identify the most error-prone modules.
Right, the 80-20. Okay, yeah. We do have some kudos as well from our social media, so quite some people liked it. So good one. There is one interesting comment. This is the testception. It's referring to the movie Inception. Test, the test, that test, the test. So it's a test within a test.
Yeah.
Right. But yeah, that's the question that we had actually. There is nothing flowing in on the platform. So thank you a lot, Adam. Thank you for sharing your knowledge. Thank you for sharing your experience as well. The Log4j example was very compelling because a lot of companies were impacted by the Log4j vulnerability issue. So yes, this is something that we should look out for. Mutation testing, that should be part of the testing procedures of the QA team and the developers as well on unit level. Thank you again. Thank you for being with us, and thank you for all the viewers to accompany us with this session. And we'll catch up later then, Adam. Take care.
Thank you very much. See you.
Bye.